So today it's foreign function interfaces. And yeah, this talk, it's like a book club based on the book of Jon Gjengset, Rust for Rustaceans. And yeah, you can get this book. And I also recommend visiting his channel. There's a very, very long and good content. And yeah, without further, I would like to give a short overview. Like the chapter 11 is a lot about crossing language boundaries, how we have to design types across the language boundaries so that we can call Rust from foreign functions or the other way around. And in this talk, I will give a small example to show some of the safety subchapters where we manually integrate a C API in Rust. So you wouldn't really do it, but we are here to learn, so we do it. Otherwise, there are good automatic tools, and I will also give a hint which tools you can use for what purpose. Okay, so I love this introduction. All code is written in Rust. It's shocking, I know. I also feel this way a lot. And yeah, as I said, after the talk, you should have an understanding how FFI works, why it works, what are the challenges, and what you can do with this. And yeah, we will start with a small motivation and then talk about the FFI boundaries for symbols and functions, or for variables and functions, how we can get types across the boundaries. We will talk a lot about safety invariants, and we will see like that's more like an overview, different crates that support FFI in the Rust ecosystem. So each of these crates deserves like its own talks, and there are talks out there from people who are much deeper in those crates than I am. And I will conclude at the end with a summary. So what is FFI? So Jon started very early with this sentence. FFI is ultimately all about accessing bytes that originates somewhere outside your application's Rust code. And yeah, that's what's now the problem is, okay, that's cool when we can use bytes that has been generated by C or something, but how can we make it work with Rust? I tried to find a bit more words for the definition. Like there was not a real definition in the bug. That was just like the first sentence. And foreign function interfaces enable code from different programming language or even compiler versions to integrate with each other. And for this, the application binary interface is needed. And this application binary interface defines how data is laid out on the binary level. So what is the state of the Rust ABI? So it's not stable, it changes. And there's a very interesting talk about if there are ideas how you can stabilize that, because that would be good for dynamic linking. Nonetheless, we don't need a stable Rust ABI because there are other ABIs around. For example, the C ABI, and that's what we will use because that's the basic of foreign function interfaces for all other languages too, for decades. And that's more of a side note for interesting things to learn. Okay. So I think the most promising use case from my perspective, because I want to write Rust, is when we can provide Rust crates like polars that have more safety or more performance than other solutions that's out there. For example, in Python, you we have a lot of modules written in C, and now we see new models written in Rust. There are also other candidates like this Open, which is an optimization engine. They actually generate Rust code and come from the Python direction. And the other way is, and that's happening a lot because the Rust ecosystem is still growing and there's a lot of code, legacy code around, and there are crates that integrate SSL, for example, in the Rust ecosystem. Also nowadays we have a Rust implementation, Rust TLS for that. Yeah, I mean that makes sense from a business perspective because maybe you want to switch to Rust, but you cannot change all your dependency at once. So it's good to have these bindings. For me, nonetheless, it feels like the first case is like a very nice cake, and in the second case, when I have to do this, I feel a bit like troubled. So the cake might explode because we have to define these boundaries, and that's mostly done by unsafe code. So we have really to be cautious what we do there. And yeah, for this, we need to understand phases of compilation. When we write source code in Rust, we transform it first in the mid-level intermediate representation. That is then compiled by LLVM to bytecode, so binary code. And that is also happening, for example, with C. So we end up in the end after compilation and code generation, at least with native languages, with some binary machine code, so-called object files. And then when we have these object files, there's a program called linker that gets them all together. And at this stage, we can mix C code or C++ code with Rust code or with Python code. In the end, most of it boils down to a C-compatible interface or application binary interface. And yeah, first things first, how can we define symbols? So in this context, a symbol needs to be defined once and can be declared as many times. Like you can define a symbol in Rust, declare it in some C libraries and use it there. Like you also know this, especially when you work with C++, with the header files, you have a lot of declarations, but there should be just one definition. Otherwise, you get the linker errors. And to access static variables over these FFI boundaries, we have the no mangle command, which is important to suppress the so-called name mangling. And we have extern. And what you see here now is like with no mangle, we define something on the Rust side, a variable that could be used in C. And in the extern block, we import some foreign debug flag. Okay. And what's important here is like static is not mutable by default, but that has also conclusions for the safety. So extern marks the symbols as declared and shifts the searching to the linker. And no mangle is very important because that ensures that a variable name matches the type names. And we have the same for functions. Here's an example from the book where we have a hello Rust function that gets exported to be used by the C side, for example. And we have a hello foreign function that may be a C function we include from a outside library. We can get more control by using, for example, export name or the link name to change really what the linker uses as name and our source code, like we in our Rust scope. So you can handle duplicate names, or don't, like when you want to obfuscate something that people cannot guess what's happening there from the Intel function name. Maybe that's a use case for this. Yeah, but this name mangling, it's quite important because, as you can imagine, when you end up having a struct with an input block or trait functions, names are not so easy to be unique. And for name mangling, there are already several implementations in the C++ world. In fact, from history perspective, a lot of compiler did like their own thing in the C++ work. In Rust, we have this mangling format v0, and I just took an example from this format website. That's how main mangling happens for a free function in the create root, right? Like we have like a prefix, and then there are some rules how the names are created, and there's also a so-called disambiguator that may be used or not. That's depending on if there are unambiguities. I think I pronounced that wrong. Okay. So that's important to end up with a nice name. Maybe to go back here, we just use with no mangle, we use the same name as the function name, and with export name we just give us a constant name by ourselves. Okay. Then linking, normally you can do it statically or dynamically. And Jon is right, there's no right choice. Depends also on your business case. I mean, a lot of businesses deploy dynamic libraries to allow features in software products. They did this because they were afraid, okay, when they have the binaries, maybe they just use the features somehow, so we don't deploy them, which is a good way. In Rust, static linking is normally this default. And when you want to see a project that uses dynamic linking, I would forward you to the Bevy engine, a game engine, and they have this dylib plugin, and it's actually helping a lot because static linking at the end takes a lot of time. But even they say like, okay, only use this during the development to reduce your iteration time on your coding, and not during release, because at the moment, because everything is like statically linked, the entire standard library will be linked in your dynamic linking library, or you get runtime errors. So you would end up with a very big dynamic linking library. Yeah, that said, I think there's also the problem when you have a DLL, you need to have like a stable ABI such that a DLL compiled within your compiler version works with the older one. I mean, there were also ABI breaks for Microsoft compilers for C, but yeah, it's a very complicated topic, and people are working on that. Okay, so how do we now allow other language to link in our Rust code, like that they can use our Rust code? For this, we have to change the crate type. Per default, we have like a special library type that also contains a lot of information about how to generate generic code, and which is compiler specific. But there are other options like static lib, and cdylib, which are static libraries as they were used in C and C++, and dynamic libraries. So you see them with .a or .so on Linux. And what you have to do is like change the crate type in your cargo toml. Another important thing, especially for the functions, you need to define what are the calling conventions, and there are a lot. Also, let's say we have a small set of defaults, and calling convention decides, are your variables in a register, are they put on a stack, in which direction, first, second, third, or reversed, and how do you return the return value? And they are the most used are extern Rust, which is the default. Like if you write nothing, it's a Rust calling convention, and otherwise there is extern C, which can also be just shortcutted with extern, which is like the really let's say, yeah, I think it also has another name, but it's not std_call. Cannot remember. In the end, you have things like fast call, vector call, this call, which just describe how you shift data in and out from functions and how you jump. So you have to be very specific about that, because now we're crossing the boundaries and we need to use the same on the Rust side and on the foreign side. Okay? And something I did a lot of research, because things change over the years, and there is this C unwind calling convention which allows that the stacks unwinds. So what happens in C++, for example, if you throw an exception, also in Rust, when you panic, the functions unwind back, and all the drop trades, like the cleanup or the structures in C++, are called in this process. And over the FFI boundaries, that is or was a lot of undefined behavior. And now you can really define, okay, we allowed this unwinding over FFI boundaries just to do this cleanup in a correct way. This is very useful for WAS interpreters. I also put some links here, because for you guys, when you really do a bigger FFI project, you probably, especially if you work with C++, you probably are interested in this. Yeah, we just learned about the first half of the chapter. And next, it's all about like, how is the data layouted in our memory? And like memory representations are, yeah, you have to specify them. And for example, for a number, for an integer, it makes a difference if this is big or little endian. That's more relevant when you work over the wire, like with the network devices nowadays, I guess. But it can also be interesting if you work on some embedded devices and switch your environment. And the same is true here for the string representation or the array representation, the vector. Like in Rust, we have values of this on the stack, like the length of a string, the capacity, and a pointer somewhere on the heap where we allocated the space for the string. And in C, is normally a C string is a so-called null terminated string. That's why here's this / null. So this is just a marker saying, okay, here's a string ends. And you can imagine when you search for the end, or you can just say, okay, I know how long it is. that has different advantages or disadvantages. So what does that mean for our FFI? There are a lot of types. And in the end, if you want to do go to FFI, you will rely on the Rust type system a lot. And we have to declare them on both sides. Like there's a struct in C, and then there's a struct in Rust, which looks similar. And there are a lot of helper types in the stud OS raw module, and also in the stud FFI module that help you to identify all this legacy things like an 4-byte integer, 8-byte integer, unsigned, and so on, and also for C string types. But there are some types that are very special. So in the book, there was this BE32 mentioned, and yeah, then it makes sense to just represent it as a vector, for example, to just use the memory. And when you use these standard containers, they have often unsafe functions like from raw parts. And yeah, what's maybe interesting for you if you're working with Windows or the Win API especially, there's a special string for that manage the UTF-16 encoding Windows did go for. So this is a lot to do this manually, but there are tools. Also, we will just look at them later and do it manually first. Maybe some flashback, because that is actually this thing with the memory representation. I had the feeling it was a lot in chapter 2 already. Like that was a chapter about it. And what we really need to do is like we write a Rust struct and we say representation C, which switches for this struct to the C ABI. And there's in the end alignment and padding. And there was a nice example in chapter 2. When you have this example here, this boolage, normally you could encode it in 1 bit. That won't work. You go for 8 bits, it's 1 byte. Okay. Now, we need 4 bytes for alignment, because here this is a 4-byte variable. So we need 3 bytes of padding, and then we end up with 8 byte. So that's how this layout was used, because CPUs can access memory much faster in this way, because you don't have to read from 2 registers. So, but it's it's important to be aware of that and use these representation C. And yeah, then there was let's say Rust enums are special. First of all, we are very precise in Rust. Like there is not the possibility to have another value in an enum. If you have bar and bas, well, we cannot encode bar and bas. And that's typically has been done in C, where often you used like a bit flag option to just store some space. DirectX, for example, this library does it a lot. Then you can end up with flags which you bitwise OR together. So that's not out of the box doable with Rust, but there's a nice crate, bitflags crate, that helps with that with procedural macros. So if you end in this problem, have a look at this crate. But much more interesting is it when you have nested types in your enums. So now we need to find a representation for this, right? Let's say bar is an integer and bus is a struct with 2 fields, A and B. So how do we represent that? In the end, we internally several types are used. Like you don't have to write that. That is what happens internally. So this food tag is just the enum without the types. Then you need for each type a own struct, and then you need a union to describe the data. And the final struct has one tag, which is the enum value, and this union of the data. So that's what we're seeing here. And this way, we can also represent complex nested enums in C structures. Okay, so allocations are often the source for curses because they can take a long time. And when you have a C library, normally you have two ways, right? Either you allocate on the implementation side or on the call side. That means in Rust or in the foreign language. And it's not allowed to allocate in one language and the other language. That will just, I don't know, I believe undefined behavior. Maybe it crashes. Maybe it crashes, not sure. And yeah, also there are two ways, like this call side or implementation sides. You find a lot of different signatures. Like you could have just a function returning a pointer, or you go with an init on buffer. You have to provide a buffer with a size, and then this this implementation just copies into your buffer. Or when you are lucky, maybe you get a hint on the size if your size is too low. That could be helpful. And yeah, what is also quite common in the world of legacy code, when you're working with COM interfaces or DirectX, you have this reference pointers. So the idea is you have a double pointer, and the implementation can then change the pointer where you're pointing at to provide you the memory. And yeah, so in the end, that are the interfaces you could end up when you implement a C interface in Rust or integrate a C interface in Rust. So let's see how can we make this how can we bind code to Rust and make it, like, let's say, maybe not safe, but we eliminate this bad smell that we may leak memory. And that's doable with the so-called RAII idiom, which means resource allocation is initialization. And for this, we use a drop trait in Rust. And we just assume now we have the init context and the free context function from an external interface. And what you just do is you write a wrapper type for your pointer. I assumed it's a void pointer here. There may be more type information. Often these interfaces end up with void pointers, and you can find it out and then cast it. So cast is another unsafe operation, but when you know the API, you may end up with something better here. And yeah, so we implement a new function, as you know it from safe Rust code or from normal Rust code without FFI. And we have to use an unsafe block to call our external function. And now we guarantee that this new is safe because we know init context will never fail, which is probably not true, but let's assume that. And we implemented the drop trait. and here we free our context. And that is called automatically when the Rust object goes out of scope, this context from C. Okay. Yeah, we moved into this area of safety, and there were like three main like three sub-chapters. Reference and lifetimes. You must ensure that when your outside code, the foreign code, the C code changes something, your wrapper type should borrow a mutable reference so that you're not accidentally also try to access it. And when you have a more complex object structure, you can also write your wrapper types in a way that they manage like the lifetime, get the invariants that are often just when you're lucky documented in the C API. And yeah, then there's this decision, are my types send or sync? And this decision is not so easy because you really need to know the C API for that. I mean, send probably works much more often than sync, but in the end, the marker types are not there on your wrapper because we have this unsafe C void pointer, right? Which is not send or sync by yeah, my idea there is first better safe than sorry. Maybe talk to the people who are really in the internals of the C API. They can help you. And yeah, that's all in the end about using marker types also for the lifetimes to ensure that you can keep up with the invariants of the C API. I think the last thing was mentioned that when the C API is very big and you have different types and everything was converted to this opaque type void, you have no support. You can just call a function with a different void pointer, like pointing to a different type, and the compiler won't help you. But when you build this FFI layer, you can actually work with new types to just wrap the C void. Okay. Yeah, there's also I will also share a GitHub link later. But first, there was a nice example in the book about an event loop. And we now will start at the top. So here we have the idea that we have an external library that starts a main loop and then gives the next event, right? And next event returns a pointer to this, a mutable pointer to this event structure. So we want to get the invariant here, so that we are not able to call, like I should have, like the invariant is, this is single threaded, okay? And obviously start main loop has to be called before next event. And we can do this in the Rust type system with just having a struct without real data, just a marker type, which is used internally by the compiler to figure things out. And then we have a freeze function for the start, which generates a event loop. And we call the start main loop and return the event loop struct. And on the struct, we implement the method for next event. And now what happens here internally is like, because of the new type, we are not send or sync anymore. And we also are sure that always start main loop is called before next event. The only problem is nobody helps you if you call start main loop several times. So maybe that's possible. Probably not. But this is like depending on the documentation of the C API here, right? Okay. I just check shortly. So I have a small example, and you can also see this on GitHub later. So I just wanted to play around and see for myself how I can implement this safety features like the lifetimes and so on, and do it manually. So I ended up with a context type, which is just a null terminated string. It has three states. It's either lowercase, uppercase, or is an invalid spec. Then we have two functions that don't that change, like are mutable. They need a mutable reference, and two query functions that can work on a immutable, on a normal borrow. Yeah, create subobject does something similar like a string slice. You just give an offset and have a substring that is working on the same memory. Yeah, and init context and free context, we already saw this before for the RAII idiom. It's just a small example, like it makes not much sense from beside learning, I would say. But let's switch to the code. So what we need is we need this C library. Here it is libc. Hope you can see it. In my case, there's an overlay from Zoom, but should work nonetheless for you. Yeah, we have the init function, the free function, context is lower, and you can see it's like a bit hard to read. Maybe I thought like maybe this is a nice quiz for you now. What is it doing here? When you know about ASCII codes and so on, you see what we're doing here. But in the end, I will also run it, and then we'll see it. So there are just very simple C functions with printfs. And what I also find very interesting is like how do we work with callbacks, right? There was also a chapter in the book, quite short, but I was just like, yeah, let's do it. And what we need for callback is like in C, we need a type def, or I mean this type def is like the FN trait in Rust. Here I just used the global variable, and now when we create a sub-object, this callback is called, and we have also the possibility to set the callback. Okay, so in this repo, we have a build script. This is here, the build.rs. And that is responsible for getting our source libc file compiled. And it also links it statically to our complete code. So we can use it. And when you integrate these automatic tools, normally you also use this build script to generate C header files or to generate Rust files out of C header files, depending on the tool you're using. So that's important for FFI. Okay. And then we have somewhere the main RS file. Oops. Let's start at the top. And yeah, what I did here is just define a module to have a bit of encapsulation. And yeah, I wrote it manually here. Like when you use tools like Rust bindgen, you could generate Rust code out of a C header file. I didn't have a header though. And yeah, so that's just these are just the bindings. And then think I also have this here on the slide. So this is now a summary. Like first of all, we had to be certain what we use, right? So this is very important at the beginning. To have this is lower can take a immutable reference, but 2 lower must take the mutable reference. Otherwise, we could change the same memory location multiple times. And yeah, we see this here. It's like it's always the same. Like you have this unsafe block. You have to work with this void pointer and to communicate with the C library. And yeah, as you can imagine, when you have a lot of those glue code, not 100 lines, but maybe so 1,000, and these tools are very helpful. And yeah, so this helps us with the invariant in Rust that we not like what the borrow checker does. We have the borrow checker actually now. And now for the lifetime, we need another phantom data because we cannot have a lifetime on a pointer. So we use a phantom data. Not sure why this is mute there. But so here we have the lifetime on our sub-object, and this is linked in the constructor or in the from function with the reference to the context. So we're not allowed to kill the context before we did get rid of all the sub-objects that look into our memory area, right? And actually what I did here is I used the pointer reference interface, which is a bit more complicated. But yeah, it's then after this is always the same, right? Yeah. And maybe I could just run it. Then you just open terminal, not external. Oh, no, the shortcut. So what this does is really we have like a context which is like a string with 26 characters. We have this toUpper method. And here I just like sometimes you find this that you have as a caller, you are responsible to check before you call a method that the object is in the right state. That's happening in legacy APIs. And here you can see, okay, I can really call toUpper multiple times and end up with a new with a, let's say, bug. So here we see the sub-object with a callback of the default. And yeah, we also still have the how to do the callback. So this is actually the code to make the setter known by your Rust code on the top. And here, this is in the main function how you can call it. And handle callback is just a function that does the conversion of the C string to a Rust string, and then use print ln. And yeah, you maybe also need to do a copy sometimes from your data. And that's also where a bit of performance can get lost, depending on how often you need the copies. Okay, let's back to the book. Pointer confusion was still open, right? And in the book, we had this idea to have a wrapper type for each C void pointer. When I did some research, I found a quite nice blog post by, hope I pronounced that correctly, Jon Gjengset, and he was advocating for some things you should do when you integrate code into Rust. And one of this was using this non-null so that you not accidentally forgot to check for null pointers. And but there was also some code about, hey, when you have like kind of an iterator, you can implement the iterator trait and give your interface a more idiomatic Rust way, right? I mean, iterator, it depends of the invariants on your C library, yeah, because maybe like we are single-threaded or everything is fine, but maybe there could be new events popping up. And when that happens during your iteration, you have a problem, right? So that is a part where you also have to watch out. Yeah, there's a lot of like maybe not a lot of open work because the RFC got stabilized. But for example, there's this function, it's called catch unwind, which allows you to write some sort of catch block. Like when you have a panic, you can just react to the panic instead of crashing. That's like a try and catch block in other languages. Like, and yeah, actually, there's open work exactly for that, to be able to catch like a C++ exception in your Rust code. That's not doable at the moment. It's actually undefined behavior. And yeah, think yeah, when you're working with a language that throws, then that's of interest for you to check this out. Okay. Yeah, it's quite long already, but we have some automatic tools. I will just give a summary, right? This Rust engine was mentioned in the book, and this is actually the generation we could have used to get the Rust code from a C code. So there's a header file, and it creates Rust bindings automatically. So this is worth a look, but as I said, probably each of this crate deserves a talk on its own. Then there's cbindgen, which is doing the other way around. I actually did work with this for a client who, yeah, used my Rust implementation in their C libraries. And the idea is that the Rust code is searched for this no mangle constructs, and it then automatically generate a header. You can use it from the command line, but you can also integrate it in the build script. That was also true for the one before. There are huge upcoming projects, like I think the DARPA, which has something to do with the defense, they want to translate all the C code to Rust. So there's a project running from the US government. Sounds good, I guess. Let's see. C++, there is, I think the most popular crate is CXX. And the nice thing about CXX is really like it tries to map those concepts of C++ and Rust that fit to each other, like RAII, resource allocation is initialization, or the templates, like part of the template can probably map to generics. Personally, I don't have real experience with this tool, but there was a very nice talk about async Rust and async C++. And first of all, send and sync is obviously a big challenge. Another thing to know is like the future type in C++ is different than the one in Rust. In Rust, you actually need to poll it, and in C++, it's not the case. It just starts when I understand correctly. And yeah, Ida Kitova did a talk about that, but there's also a blog post about yeah, this interop with async Rust and async C++. What about Python? Python is probably, for some people I know, the most interesting language. And we already saw on one of the first slides this open, which is like generating Rust code, like really text generation and then compiling. with the use case that they want to have a model predictive control optimization on embedded devices. And the researcher, you can just do his thing in Python, and it's blazingly fast. And the other thing, which is quite huge, I think, is Polar, which is a data frame library similar to Pandas. And for this, Pio3 was used, and you will actually find, oh, what was it? Yeah, we will find actually a lot of things about Pio3. I think there was also a talk on no, that was a tutorial. I remember I didn't find it. The tutorials were not recorded, but this was on Rust Nation. And there the idea is really in Rust you mark with the procedural macros, some functions. You can describe what should go in my Python interface. And then you use the Rust implementation as a Python module. So when that's your thing, check out the user guide. And yeah, there were also some best practices mentioned, especially that you use this suffix and decouple your bindings from your normal crate, like have two crates. And what we did here, this manual coding, and you will get a GitHub link, is yeah, it's yeah, I don't think it's worse beside from learning nowadays. The Rust ecosystem is quite far, I have the feeling. Yeah, I mean, what we do here is using different programming language, and people could now say, okay, I can have a JSON backend and a Rust backend talking to each other, and we use JavaScript backend. We use protobus, for example, for the serialization. Yeah, it solves a similar problem, but it's much, much slower, right? But in the end, FFI is only doable when you can link together the code in some way. So that's how I differentiated that. Okay. This is the last slide. No, the second last slide. Okay. We did a lot. I hope you enjoyed the talk. I have a lot of references here that you can check out. And how can I open the chat? Ah, you know, see the chat in big, right? In a second. Or not? Were there any questions?
Feel free to talk with your microphone. Don't be shy. Any questions? No. The talk was so good. You explained everything so well.
I think actually, to be honest, it is a quite dense material. Like the chapter in the book is quite maybe I can just share. I should have done this, but I'm always a bit like you think differently, right?
I've done some FFI stuff, and for fun, I try to wrap the Win32 API, Linux sort of X11 libx API, and Vulkan, and yeah, there's a lot of shotguns, especially around with memory management and memory ownership.
Yeah, it's very hard to really understand. You really need to understand that, and then the Rust code you write is probably also quite let's say most people when they just do application coding in Rust, let's call it that way, there's not so much you have to think about how you put your lifetimes together. I had the feeling in FFI you need a lot of advanced techniques, really apply them. So
there's a question on the chat. The question is, since all Rust values are stack allocated, should I restrict myself to box value whenever I do see Rust interop? I can actually answer that.
I think you cannot share stack values over the
you can.
You can share a pointer on the stack, but what happens when it works? Okay, can you answer?
Yes. So yes, you can, because what you're doing is, if you're talking to C, you're matching the C's ABI, right? And ABI has certain rules about what parameters are passing registers, what parameters on the stack, and so forth, like that. And the Rust compiler would take care of that, because as soon as you do the extern, it will then do the conversion for you and stuff like that. Now, if you're talking about structures that are on the heap, right, then you can leak a box and then pass that to the C interface, and then when you get something back, if you get something new back, you can then generate a box out of that, and take ownership. Maybe well, you can do it with vector arrays from the raw parts stuff, but you don't need to. You can pass integers into it as well. You can pass structs, as long as your struct is represented. Use a repr C stuff like that. Yeah, like that slide. You'll be fine.
Yeah, that's what I needed some time, but yeah, that's really what you have to do for the stack types, right? To have this one-to-one mapping that this struct like exists on the other side in C2.
Mm-hmm.
And yeah, what you said with the leak, that is also quite important. Otherwise, you can just drop your values, and then the FFI still has them, and you get a memory access error as soon as the FFI methods or the foreign interface access them.
Yes.
So that's very important when you use box, or I think also with VEC, all these owning types. When you move ownership over the FFI.
Yeah, but if the lifetime of an object you're passing to your structure, your C function is longer, then you're fine, right? Yeah, so the repr C it's not 100% required, but you better use it, because I think in that example, if you didn't have it, that structure would be reordered and reduced to 16 bytes, which is really cool when you're dealing with Rust and code, because you want that efficiency of memory. But it's the worst thing that can happen if the ABI on the C library is expecting bytes and certain offsets in your structures. You don't want Rust pulling the rug from under you on that one. Is there any other questions? Going once, going twice, 3 times.
Yep.
Okay, we're done. Thank you so much, Tim.
Everyone. Yep.
Thank you for putting these slides together and making me a believer that orange works on slides.
Yeah, I like the colorful stuff. All right.
I will stop recording now, and have a great evening. Thank you so much.